Metasurfaces are ultra-thin, engineered structures that manipulate light in extraordinary ways, surpassing the capabilities of traditional optics. Imagine a tiny, flat surface covered with thousands of microscopic antennas, each smaller than a grain of sand and intricately arranged. These antennas act like miniature traffic controllers for light waves, directing their paths, changing their speed, and altering their behavior. To understand this, think about a traditional lens, like those in glasses or cameras, which bends light to focus it. Traditional lenses are like thick, curved pieces of glass that work by gradually bending light through their bulk. In contrast, metasurfaces achieve similar effects, but with a layer as thin as a sheet of paper. Imagine you have a transparent sticker covered with tiny, invisible gears. When you stick it on a window, the light passing through the window is redirected by these gears to focus on a specific spot, just like a bulky lens would, but without the thickness. One fascinating application of metasurfaces is in creating flat lenses, which can replace traditional curved lenses in cameras, telescopes, and even eyeglasses. These flat lenses are not only much thinner and lighter, but can also correct for various optical problems that traditional lenses struggle with, like chromatic aberration, where different colors of light are focused at different points. Imagine swapping out the heavy lens of a camera for a sleek, ultra-thin film that provides even better clarity and precision. Metasurfaces can also be used to create invisibility cloaks, bending light around an object to make it invisible to the observer. This is like how water flows smoothly around a rock in a stream, leaving the rock unseen from the water's surface. By manipulating the light to flow around the object, metasurfaces can make it appear as if the object isn't there at all. Another exciting application is in holography. Metasurfaces can create detailed holograms by precisely controlling light to produce three-dimensional images. Think of it as using a flat, thin screen that can project complex 3D images into the air, like a scene from a science fiction movie. In telecommunications, metasurfaces can steer and focus laser beams with high precision, improving the efficiency and capacity of data transmission. Imagine a lighthouse that can not only rotate its beam, but also shape it into different forms, sending signals to multiple ships with pinpoint accuracy. Overall, metasurfaces represent a groundbreaking advancement in optics, providing new ways to control and utilize light with unparalleled precision. This technology opens up a world of possibilities, from advanced imaging systems and sensors to revolutionary communication technologies and more. Imagine lenses thinner than a human hair, capable of manipulating light in ways we never thought possible, creating new possibilities in optics. This is the promise of metasurfaces, a revolutionary technology poised to transform optics and photonics, pushing the boundaries of what we can achieve. But what exactly are metasurfaces? And why are they so significant in the world of science and technology? Metasurfaces are essentially two-dimensional arrays of nano-sized structures, meticulously designed to interact with light in extraordinary and precise ways. Think of them as tiny antennas, each engineered to scatter, absorb, or transmit light of specific wavelengths, tailored for specific applications. By carefully arranging these nanoantennas, scientists can create metasurfaces that manipulate light with unprecedented precision and control. The beauty of metasurfaces lies in their ability to control the phase, amplitude, and polarization of light properties that govern how light interacts with matter, enabling new functionalities. This control allows us to bend, focus, and shape light in ways that traditional lenses and mirrors can only dream of, opening up new research directions in optical design.
Imagine a lens that can change its focal length at the flick of a switch, or a mirror that can selectively reflect or transmit different colors of light. This is the promise of electrically tunable metasurfaces, a new breed of optical devices that combine the precision of nanotechnology with the versatility of electronics. These devices are paving the way for innovations that were once thought impossible. Unlike their static counterparts, electrically tunable metasurfaces can dynamically adjust their optical properties in real time. This means they can respond to changing conditions almost instantaneously. This dynamic control is achieved by integrating the metasurface with materials whose optical properties can be altered by applying an electric field. This integration is key to their functionality. One such material is graphene, a one-atom-thick sheet of carbon atoms arranged in a honeycomb lattice. Graphene is renowned for its strength and flexibility. Graphene's claim to fame lies in its remarkable electronic and optical properties. It is highly conductive and transparent, making it ideal for optical applications. By applying a voltage to a graphene layer integrated with a metasurface, we can change its electrical conductivity, which in turn modifies how it interacts with light. This process is both efficient and highly controllable. This ability to electrically tune the optical response of graphene opens up a world of possibilities for creating active metasurfaces that can switch, modulate, or steer light beams with unprecedented speed and precision. The potential applications are vast and varied. Imagine high-speed optical communication systems that can transmit data at lightning-fast rates, or adaptive optics systems that can compensate for atmospheric turbulence in real time. These systems could revolutionize telecommunications and astronomy. These are just a few examples of the transformative potential of electrically tunable metasurfaces, a technology poised to revolutionize the way we interact with and harness the power of light. The future of optics is bright, and electrically tunable metasurfaces are leading the charge.
The quest for dynamic control over light has led scientists to explore a fascinating array of materials, each with its unique properties and potential applications in tunable metasurfaces. These materials are at the forefront of modern optical technology. From the mesmerizing world of liquid crystals to the transformative abilities of phase-change materials, the possibilities are as vast as the electromagnetic spectrum itself. These materials offer a new realm of opportunities for innovation. Liquid crystals, as their name suggests, exist in a state of matter that lies somewhere between a liquid and a solid. This unique state allows them to exhibit properties that are not found in conventional materials. They possess the fluidity of liquids but exhibit a degree of molecular order, making them highly responsive to electric fields. This responsiveness is key to their application in advanced optical devices. By integrating liquid crystals into metasurfaces, we can create devices that can dynamically alter their optical properties, such as their refractive index, by simply applying a voltage. This capability is crucial for developing next-generation optical technologies. Phase-change materials, on the other hand, have the remarkable ability to switch between different states, amorphous and crystalline, when subjected to heat or light. This switching mechanism is fundamental to their functionality. These different states exhibit distinct optical properties, allowing us to create metasurfaces that can selectively reflect, transmit, or absorb light depending on their phase. This selective control is essential for various optical applications. And then we have graphene, the wonder material that continues to amaze us with its versatility. Its unique properties make it a standout material in the field of advanced materials science. As we discussed earlier, graphene's optical properties can be readily tuned by applying an electric field, making it an ideal candidate for creating high-speed, electrically controllable metasurfaces. This makes graphene a pivotal material in modern optics. The exploration of these and other novel materials is opening up new frontiers in the field of tunable metasurfaces, paving the way for smarter, more adaptable optical devices that can sense, adapt, and respond to their environment in real time. This ongoing research promises to revolutionize the way we interact with light and optical technologies.
By harnessing their unique optical properties, we can develop imaging systems that provide higher resolution and better contrast, enabling earlier detection and more accurate diagnosis of diseases. This could revolutionize healthcare, making medical procedures less invasive and more effective. But the potential of metasurfaces doesn't stop there. They are also being explored for use in augmented and virtual reality devices, providing more immersive and realistic experiences. By controlling light with incredible precision, metasurfaces can create displays that are brighter, more colorful, and more energy efficient. Beyond these applications, the future potential of metasurfaces is vast. Ongoing research is uncovering new ways to integrate these materials into everyday technology, from smart windows that can adjust their transparency to wearable devices that monitor health in real time. The possibilities are limited only by our imagination. The exploration and development of metasurfaces are paving the way for a future where our interaction with light is more sophisticated and versatile than ever before. As scientists and engineers continue to push the boundaries of what is possible, we can look forward to a world where metasurfaces are an integral part of our technological landscape, driving innovation and enhancing our quality of life. Join us as we continue to explore the fascinating world of metasurfaces and their transformative potential. The journey is just beginning, and the future is brighter than ever. This makes it difficult to produce metasurfaces at a scale that is economically viable for widespread commercial use. Scalability is another significant issue. While metasurfaces have shown great promise in laboratory settings, scaling these technologies for industrial applications remains a challenge. The transition from small-scale prototypes to large-scale production involves numerous technical and logistical obstacles that must be addressed. Material efficiency is also a critical concern. The performance of metasurfaces heavily depends on the materials used. While there have been advancements in developing materials that can manipulate light effectively, there is still a need for more efficient, cost-effective, and durable materials that can withstand real-world conditions. Despite these challenges, the scientific community is actively researching potential solutions. Advances in nanofabrication techniques, such as electron beam lithography and nanoimprint lithography, are showing promise in making the production of metasurfaces more efficient and scalable. Researchers are also exploring the use of novel materials, like metamaterials and hybrid structures, to enhance the performance and durability of metasurfaces. Moreover, interdisciplinary collaborations between physicists, engineers, and material scientists are driving innovation. By pooling their expertise, they are developing new methods and technologies that could revolutionize the way we design and fabricate metasurfaces. The journey of metasurfaces is one of both immense potential and significant challenges. While there are hurdles to overcome, the ongoing research and development efforts are paving the way for a future where metasurfaces can be integrated into everyday technology, transforming industries, and improving our quality of life. As we continue to explore the fascinating world of metasurfaces, we must also acknowledge the importance of addressing these challenges. By doing so, we can unlock the full potential of this revolutionary technology and ensure that it becomes a cornerstone of our technological landscape. Join us as we look forward to the future of metasurfaces, where innovation knows no bounds and the possibilities are endless. As we reach the end of our journey through the fascinating world of metasurfaces, from the revolutionary flat lenses pioneered by Picasso to the intricate structures and materials that make up metasurfaces, we've seen how these tiny yet powerful devices are set to transform the field of optics and photonics. Their ability to manipulate light with unprecedented precision opens up a world of possibilities, from advanced imaging systems to next-generation communication technologies. We've also delved into the exciting realm of electrically tunable metasurfaces, where liquid crystals, phase-change materials, and graphene play pivotal roles. These innovations pave the way for dynamic and adaptable optical devices that can respond to changing conditions in real time. Despite the significant challenges in fabrication, scalability, and material efficiency, the relentless efforts of the scientific community are driving progress. Advances in nanofabrication techniques and the development of novel materials are gradually overcoming these hurdles, bringing us closer to widespread commercial adoption. Looking forward, the most promising research directions include refining fabrication methods to make them more cost-effective and scalable, exploring new materials that enhance performance and durability, and fostering interdisciplinary collaborations to drive innovation. The future of metasurfaces is bright and full of potential. As researchers continue to push the boundaries of what is possible, we can expect to see groundbreaking breakthroughs that will revolutionize industries and improve our daily lives. Stay tuned for more exciting developments in the world of optics and photonics, where the only limit is our imagination.